Hello everybody, in this video we're going to be discussing the concept of inverse functions, okay? And inverse, this is a word we're very probably familiar with in mathematics, but keep in mind that inverse, when we discuss the inverse of something, it's like the undoing of something that we've already done. So I always kind of say it's like, when you buy a vehicle, you have drive on it, of course you would want reverse. We want to be able to undo what you've done. Or in a, more concrete sense, if you talk about mathematics, if you say we wanted to undo addition, we could do subtraction. If you wanted to undo multiplication, we would use division, and so on and so forth. But you have to realize a function, remember, a function is just simply a rule, and we typically use function notation. We call it f of x, okay, or f in this case is the name of our function. But we're going to go ahead and start with this function here. F of x equals 2x minus 6, and because this is a really simple linear function, we're very familiar probably with how this behaves. It has a y-intercept of -6 and a slope of 2, and actually, you can see that I've graphed it over here. Here's our y-intercept of -6, and it goes up 2 over 1, and yeah, that's what it does, okay? So keep in mind, okay, we talk about a rule here. This function, what it does is it takes inputs x, okay? So why don't we write this as input-output notation for just a moment here. It's going to take our input values, or our domain values, under this rule f, okay? So we've got, we'll change colors here, f, and what it does is spits out a bunch of output values, or f values, with that given input x. So for example, if we were to plug in, say, I don't know, 0, 0 would be doubled, and then we would take 6 away from it. Of course, that would map onto -6. Or maybe we plug in, 2. 2 times 2 is 4 minus 6, okay? So this would map over to -2, and this would continue to happen for any input values. 5 doubled minus 6 is 4, okay? So this is just a small list of inputs and outputs. Of course, we could input all real numbers into this function, but for the sake of what we're discussing today, we're talking about inverse functions. It would be a function in which it would undo what we've just done. So why don't we'll switch colors here. We'll go to something more prominent, like a fuchsia or red. There we go. We say red is the color of power, correct? So let's say we had an inverse function, okay? And for the sake of this argument, we're going to, or for the sake of for math in general, we're going to write the inverse function like this, okay? And, this doesn't mean the same thing as 1 over f positive 1 of x. That's not what we mean, and not the reciprocal, okay? However, what we mean is f inverse of x. So you can know this, we read this as f inverse. We can write that f inverse is the way we pronounce this. And f inverse's job, its only function, mind the pun, is to take the outputs, okay? So we went from input to output last time. What we probably want to do here is take the outputs that we got in the last function and go back to the original inputs. Maybe that's what we want to do sometimes. We want to go from what we just did, undo it, and get back to where we started, okay? So I think it would be nice to write out in function notation. By the way, this is f inverse in red. In function notation, or roster notation, sorry, these inputs that we used. So let's say we had f. For the sake of f, we know that when we put in 0, we had an output of -6. When we put in 2, we had an output of -2. And when we put in 5, for example, we had an output of 4. Now, what I want us to realize is this. If f inverse, its job is to take the original outputs and map them back onto the original inputs, what you notice is this. If we were to, say, have a function, f inverse, when we plug -6 into it, okay, when we plug in -6, which keep in mind was the output of the original, it gets mapped back over to 0. -6 back over to 0. If we were to take the output -2 and plug it into the undoer function, it would send it back to the original input of 2. And last but not least, if we were to take the output, the original output of 4, and plug it into the inverse function, it says, well, you must have started at 5, okay? So the inverse function here and the original function f, if you're looking at this, what I really want you to realize is all we've really done is taken all the original x's and y's and swapped them around, okay? That's all we did. So I guess the definition of an inverse function, you can look at it this way. It basically is the same as the original function. It's just that our domain and range have simply flipped, okay? And so, this has certain graphical properties, and we'll kind of analyze that here in a minute. But basically, yes, f inverse just takes the original outputs and maps them back onto the original inputs. So really all we've done, again, is switched out the x and the y, or the domain and range. Or maybe I should say it this way. If we've switched around the domain and range from here to here, and here to here and here to here, then I think it would be fair to say this. All we really did from the original function to the the inverse function is swapped out our x and y, swapped out our domain and range. Okay. So if that's the case, let's go ahead and go back to our original function, which by the way was f of x equals 2x minus 6. We want to define an inverse function. So now keep in mind, this was like our original y here. We're writing f of x, but if to find the inverse function, all we do is switch the domain and range, here's going to be the rule. Finding inverse functions. So if you're like taking notes or whatever, inverse functions, here's what you want to write. Basically, the steps we go through algebraically to find inverse function is this. Step 1, swap domain and range. I'm going to write it a little bit differently. I'm going to write swap all x's and y's. So whatever was an x before becomes a y. Whatever was a y before becomes an x. Step 2 is going to be this. Solve for y. Okay. So now keep in mind, I haven't gone into whether or not the inverse of a given function is itself a function, which by the way requires one-to-oneness. Every x goes to 1 and only one y, and we'll discuss that with the horizontal line test, not the vertical. But let's take this for a test drive here. Okay, so the original function is y equals 2x minus 6, or f of x equals 2x minus 6. We said in order to find the inverse of this function, let me clean that up a little bit there. 2x minus 6. What we'll do is this. We'll do the inverse in red here. We will switch all x's with y's and y's with x's. So 2y minus 6. So x equals 2y minus 6. By definition, what I can tell you is this. Right now, what I have just designated is the inverse function of the original. We have switched all the inputs and outputs around. It's just that we tend to like things written in y as a function of x notation, okay? So what we're going to do now is we're actually going to solve for y as we kind of designated down here on our protocols. So let's do that. You know, we added 6 to both sides here, add 6. We end up with, sorry, I'm going to use reflexivity here, 2y on the left now is equal to x plus 6. And then we could simply divide everything by 2. And we get y equals 1/2 x plus trace, okay? So now I've designated this, but let me be a little bit more clear on this. Instead of y equals 1/2 x plus 3, we better be clear that we're telling our audience that this is f inverse, or the undoer function of the original function. Okay, so f inverse of x equals 1/2 x plus 3. And for just a moment, we're going to pop back over here because I do want to graph this. So if we were to type in 0.5x plus 3, there is our inverse function. You can see it, you know, passes through positive 3 on its intercept and up 1 over 2. And you'll notice, you know, inverse functions, at least for linear things, you know, have slopes that are reciprocal to one another. But the fact of the matter is, some special properties occur here, okay? And so, in order to kind of better illustrate this, let's go back to, say, these original points that I had, you know, like, kind of found here. If for example, we were to graph the original f of x, those points, at least, that I had plugged in, you'll notice that I had used 0, negative 6, so we say, okay, so 0, 1, 2, 3, 4, 5, negative 6, there she is. 2, negative 2, so over 2, down 2 was in the original function, and, you know, 5, comma 4, so over 5, up 4, and there that one is. And of course, you know, we've got a line that passes through these, but let's just say these points for now. If I were to graph now the inverse function in red, we had negative 6, comma 0, 1, 2, 3, 4, 5, 6, negative 6, comma 0. Excuse me, negative 2, comma 2, which is up here, and 4, 5, 4, 5. Now I've done this for a reason, and that reason is essentially this. When you graph inverse functions, if all you're doing are taking the original x's and y's and just swapping them out, what we can say is basically this. Then these points are reflected or symmetrical about a specific line, and that line is going to be the identity function. The identity function. Now, that's a special name for basically y equals x, where we have an intercept of 0, and it proceeds up 1 and over 1. But you would notice that each of these points are equidistant to this center line, and thus we could say exhibit symmetry about this center line. So one way to recognize inverse functions is to check for symmetry. Symmetry, you know, or reflection about not symmetry, reflection, about y equals x. That is a big thing to look for. So now going back over to the very, very clean graph that we've drawn before, you can easily see this if I pop this line y equals x back in there, maybe. There it is, okay, and I've got it kind of a dotted line. Okay, so we have this graph, the original function f of x here, and its inverse function, of course, f inverse of x is reflected about this line. And we could simply prove that these were inverses by 1, showing that they are reflected about this line. 2, we could maybe pick on individual points, like if you can see my mouse here, this would be the point 3, 0. If 3 zeros on the original function, then on its inverse, 0, 3 must also lie on that function. And this relationship occurs for, the entirety of both of these graphs here. You can see this. But a good way to check to see if two functions are inverses is simply to graph them. Now, that can't be the only way. I suppose we could find an algebraic way to do it. And another simple way to do it would be, well, let's just plug in a bunch of inputs into the original function and look at the outputs. And then let's select a desired output. So for example, -6. We know that if what we found over here, which is f inverse of x, if it is truly the inverse of the original function, then when we plug in -6, which was an output of the original, it should map back onto the original input. So checking a few of these, we could say, okay, so f inverse of -6, well, that would be 1/2 times -6 plus 3. We know that 1/2 of -6 is -3. -3 plus +3, and we get an output of 0. So that is, when we took the original output of the original function, -6, and plugged it into the inverse, or the undoer function, we got back to the original input, 0. Okay? And this would work with checking any of our original outputs and plugging them back in. So one way to check for inverses is to graph them and check for symmetry about this center line, okay, y equals x. Another way is to, let's take some original output values, plug it into the inverse that we found, and see if they map back onto the original inputs. The last way to check is going to be this, and I'm going to try to make this brief here, but basically, the definition of inverses is that they undo each other. So say f inverse, okay? Now keep in mind, f inverse, again, it says, give me the outputs of the original function, and I'll get you back to the original inputs. So what if I were to take the f inverse of an original output value? We've seen that, like for example, we plug in -6, we get back to 0. -6 was a y value for the original function. In other words, -6 was an f of x value of the original function. It seems to me that if what we said is true, that every y value we plug into the inverse, we get back to the original x value, then what if we were to plug in f of x in general, okay? The original y values expressed as f of x into the inverse function. Then it should send it back to the original, in general, x values. So what I'm about to illustrate here is this. We say f inverse of the original outputs, which were f of x values. Let me clean that up. F of x values. What you find out is map back onto x. Okay. I'm also going to tell you this. That would be the same thing as if we took f of f inverse of x. Okay. The outputs of our inverse function plugged into the original should go back to the original inputs of the inverse function. Now I know that sounds crazy, but let's take a look at what would happen here if we found, say, f inverse of f of x. So now we have our two functions. We have f of x, the original 2x minus 6, and we have f inverse of x, which was 1/2 x plus 3. So now composing these functions, we say we want to find, say, f inverse of f of x. So what this means is, for our function f inverse of x, everywhere we see an x, we're going to plug in this, f of x, the original outputs. So f of x here, we know what f of x is. F of x was 2x minus 6. So for the sake of, there we go, we got blue. I'm going to write f of x here for just a moment, but we know what f of x is. We know that f of x is 2x minus 6 plus 3. So now distributing our half, you see that -1/2 times positive 2x becomes negative x. Negative x. Ooh, have I made a mistake here? 2x minus 6. Oh, this half is not negative. I was like, wait a minute, sorry, not negative there. Forgive me, it is positive. But a half times 2x would just simply be x. Distributing the half to our negative 6, we get minus 3. And then, of course, we have this plus 3 on the end. So x minus 3 plus 3 turns out to be just x. So generally speaking, we can take the original outputs of the original function, plug them into the inverse function, and it spits out the original inputs, which were, in general, x values. Okay? So in the next video, we're gonna go through all three of these checks, but we're gonna run through some examples. But that is the definition of an inverse function. It takes the original outputs of a function and sends it back to the original inputs.